Endurance performance is complex and is limited by multiple physiological systems working together. We often think of fatigue as a muscle problem, but modern exercise physiology shows that it is an integrated response involving the cardiovascular system, metabolism, neuromuscular function, and even the brain. Today, I'll break down the most well-supported limiting factors using primary peer-reviewed data. I'll start with traditional determinants such as VO2 max, lactate threshold, and running or cycling economy, and then move into more modern concepts like critical power, central versus peripheral fatigue, glycogen depletion, oxygen delivery limits, and the role of heat and brain temperature. By the end, you'll see that endurance performance fails not because one system collapses, but because several systems reach a point of unsustainable physiological strain. One of the most influential studies in endurance physiology is Coyle et al. In 1988, which identified three major contributors to endurance performance. VO2 max, or maximal oxygen uptake, provides an upper limit on the body's aerobic capacity. It defines the ceiling for sustainable power or speed. And next is the lactate threshold, which tells us how much of that VO2 max an athlete can actually sustain without accumulating lactate at a rate that forces them to slow down. Two athletes may have the same VO2 max, but the athlete who can operate at an 80 to 85% of VO2 max instead of a 60 to 65 will perform dramatically better. Finally, movement economy refers to how much oxygen it costs to maintain a given pace. Small improvements in economy, such as running with smoother mechanics or cycling at an optimal cadence, can significantly enhance endurance performance. Together, these three variables explain a lot about why some athletes outperform others, but they do not fully capture the mechanisms that ultimately limit performance during intense or prolonged exercise. Endurance performance depends heavily on oxygen delivery. That is, how efficiently oxygen can be transported from the atmosphere to the mitochondria inside the muscle. Gonzalez Alonso and Calbit showed that oxygen delivery is what ultimately limits VO2 max, not the muscle's capacity to use oxygen. Here's why. Cardiac output is the biggest limiter. Even elite athletes' hearts have a finite ability to pump blood. Once that ceiling is reached, oxygen delivery cannot increase further, regardless of muscle demand. Hemoglobin concentration determines how much oxygen each liter of blood can carry. This is why altitude training or anemia significantly affects endurance performance. Lastly is peripheral extraction. The amount of oxygen muscles can pull from the blood eventually plateaus. There comes a point where muscles simply cannot extract more oxygen even if more were available. This means endurance failure is not purely muscular. It begins in the cardiovascular system when oxygen supply can no longer meet metabolic demand. One of the clearest performance limiters is muscle glycogen availability. Bergstrom's classic biopsy study demonstrated that endurance capacity is tied directly to how much glycogen is stored in muscle before exercise starts. When glycogen levels are high, athletes can maintain a given workload of long periods. But when glycogen is low, time to exhaustion drops dramatically, even if oxygen availability is normal. Glycogen depletion reduces the rate of ATP resynthesis, which is essential for sustained muscle contraction. It increases reliance on fat oxidation, which cannot support high-intensity workloads on its own. Low glycogen also increases metabolite accumulation, which interfere with calcium handling and reduce force production. Thus, glycogen acts as an internal fuel gauge. When it drops too low, performance deteriorates rapidly, regardless of effort or motivation. The critical power CP model is one of the best tools for predicting endurance limits. Poole and colleagues define critical power as the highest intensity at which the body can maintain metabolic steady state. Below CP, oxygen uptake, lactate, and muscle metabolism stabilize. Above CP, they become unstable. VO2 rises, lactate accumulates rapidly, and acidosis increases. Once above CP, exhaustion is a matter of time, not willpower. CP also includes a finite work capacity called W, which represents the anaerobic reserve above CP. This reserve depletes predictably. Once W is gone, the athlete must slow down below CP or stop. This model is widely used in cycling, running, and rowing to determine optimal pacing and training intensity. Peripheral fatigue originates in the muscle but affects the entire neuromuscular system. When metabolite levels rise, they activate sensory nerves called group 3 or 4 afferents. These nerves send distress signals to the brain indicating that the muscle is under heavy metabolic strain. Amon's 2006 study found that this afferent feedback increases perceived exertion and reduces central motor output. In other words, your brain voluntarily reduces force production to protect the muscle from damage. This mechanism means endurance performance is limited not simply by running out of energy, but by protective feedback loops designed to preserve muscle integrity. Central fatigue refers to a decline in the nervous system's ability to recruit motor units. This is not due to muscle failure. It is the brain deliberately reducing drive. In a Mons 2009 study, researchers manipulated afferent feedback and showed that altering sensory input changed how much voluntary activation subjects could produce. When feedback was blocked, participants pushed themselves harder, but at the cost of greater muscular disruption. This suggests the brain imposes a governor to prevent catastrophic failure. Fatigue is therefore not just about physical limits, it is a protective, centrally driven regulation to maintain homeostasis. In hot environments, performance drops even when hydration and carbohydrate levels are controlled. Nebo and Nielsen's 2001 study demonstrated that rising brain temperature is a critical limit of endurance. As brain temperature increases, perceived exertion rose dramatically, voluntary activation fell, and athletes slowed or stopped despite adequate oxygenation and fuel. This shows fatigue in the heat is centrally mediated. The body can sustain the cardiovascular and metabolic demands, but the brain acts preemptively to prevent overheating. This is why even elite athletes slow significantly in extreme heat. The limiting factor is not muscle, but neural tolerance to elevated temperature. When we integrate all these findings, a clear picture emerges. Endurance performance is limited by the interaction of multiple systems, not a singular failure point. Cardiovascular limits constrain oxygen delivery. Metabolic limits, especially glycogen depletion, reduce sustainable intensities. Critical power defines the metabolic tipping point. Peripheral fatigue increases afferent feedback. Central fatigue reduces voluntary drive as protection, and heat places additional strain directly on the brain itself. Performance collapses when one or more systems hit a threshold beyond which homeostasis cannot be maintained. Endurance success depends on how well athletes can push these thresholds outward through training, fueling, acclimation, and pacing. Here are my references, and thank you for listening.